I'll just... All right, so this, we're gonna call this a lamina, all right? A lamina is like a flat sheet where you're gonna kind of neglect the thickness of it because, I mean, really this is not a, this is a solid, right? This is a three-dimensional solid, but let's just look at it in terms of it being like two-dimensional only, right? There's no depth to it, which doesn't make a lot of sense, but let's just do that, all right? We call this a two-dimensional lamina. Now, this lamina has a mass to it, right? It has some mass, and we would like to see if we can find the center of mass of this. Where do you think the center of mass for this is? Right in the center of it? Well, there's an easy way to find centers of mass of things, like physically, if you have them in your hand, and that's all you have to do is you can just take it and suspend it from one point and then just drop a plumb line. So drop a string and then draw a line where that string is. And then you just pick some other point and then do the same thing. And you drop a line again. And then just to be safe, pick another third point and then drop a line again. And they should all intersect at the center of mass. All right? That's just an easy way to find centers of masses of things like this. Now, what we would probably all agree upon here is that if I took this, whatever mass it has, if I cut it in half, right down the middle, that we would have equal masses, right? That they would be the same. If you did that, if you believe that, then what you're assuming is that this is what we call a homogeneous lamina. Homogeneous meaning that it's the same throughout the entire material, everything is the same, right? So the mass doesn't change as you move around. Or I should say, like, the density doesn't change. What we're interested in is things that are non-homogeneous. So what if this was a lamina where as you move along at different places on this lamina, you have a different density. So maybe over here, the material is more packed in, so you have it's dense, more dense over here, and maybe less dense over here. That would change your center of mass, wouldn't it? And if you cut it in half, it would no longer be equal on each piece, right? Because you would have varying density. Kind of make sense? So the goal of what I'm going to do here is that we are going to take a lamina that has varying density, and we are going to find its center of mass, and we're going to find its moment of inertia. And I'll explain a little bit about what those are and what they mean once we get to them, right? That's the goal. So some introductory stuff here. Has anyone done moments or centers of mass a little bit? Yes? Okay. With integrals? No? Not with integrals? No? Usually the object is pretty uniform though, right? They give you something that's like a nice object or no? Yeah? Where is it? There. I don't know how I lost it. Okay, so a couple of things to get out of the way first. Density, by definition, is the mass divided by volume. But we are going to treat this, again, this lamina, as if it's only two-dimensional. So we are going to say that the density is the mass divided by the area instead of volume. We're going to act like the dimension this way is like 1. It's like this, the thickness is a 1, so the volume and area are equivalent. Does that kind of make sense to you? Like if I tell you, you know, what's the area of this little patch on here, right? Imagine that, or what's the volume of that patch? Imagine that this was 1 unit thick. Then the area would be equivalent to the volume. Make sense? Numerically, they're the same numbers. All right, so if you can accept that as a definition for density, and you can accept that this is a lamina living on a flat sheet of paper like that, XY, then we want to suppose that the density, or the mass per unit area, is variable, so that the density changes at each point. You go to a different point, you have a different density. Non-homogeneous lamina. Then the total mass of the lamina is the sum of the mass at infinitely many infinitesimal rectangles within the lamina. Okay, so let me explain this in better terms. Let's go back to that lamina, and let's imagine we take that lamina and take a small little infinitesimal thing. Hey, we've done this before, haven't we? A little infinitesimal patch. Let's call this side dx, call this side dy. Then that right there is dA, right? We called that in the past dA. That has a little area to it, right? Let me write these things down better. Density is mass over area. So that means if I multiply both sides, the density times the area will be the mass. So if I wanted to know the mass of that little infinitesimal little piece, right? If I want to know the mass of this little tiny little piece in here, if I want to know what its mass is, then what I would need to know is what's the area of that little patch times the density at that point. So someone would have to provide me the density at that point, and then I could give you the mass. And if I do that at every single one of these little infinitesimal patches and add them up, I will get a total mass, right? It's like a mass at each infinitesimal little patch we will find a number for, and then we add them all up, and that gives you the total mass of the lamina. Does that make sense to you? Like how this is going to be a double integral? So going back here, highlight this. So I give you a lamina, okay? I give you the lamina, I give you the region, whatever it is, the shape of it, and then I give you the density function. I have to provide you, I tell you, hey, at every point, what's the density? If I do that, then the mass of this lamina will be the double integral over the region D of the density function times the dA, which is the area. So it's the density times area, which is a mass. The sum of the masses is what you're doing here. Okay? I like to look at it this way. I have a picture for you. Where's my picture? Imagine that that's your lamina, okay? Do you see the shading of it is kind of implying that it's got a different density at different places? So let's say that over here, the density is really, really small. So things are not packed in very much. And over here, it's really dense. One way we could kind of visualize that is that at this, let's say at each point here, we assign a number for its mass, and make that like a height coming out at you. Okay, so like whatever the mass is here, measure it, and then make that come out towards you as like a z-coordinate, and do that at each point. Then if you just turn this and look at it like this, then the volume of this is the mass of the object. Yeah? Because you're just taking each little point that was on the ground and you're assigning a mass at each point. And so summing up all those masses will give you the total mass of the object. So it's everything we've been doing, except now our surface on top and our region on the bottom have somewhat different meanings to them. Like just physically they have different meanings. Which is why math is the tool, right? Math is the tool. We learn how to do double integrals, and then we start using them in different fields depending on what we're trying to accomplish, right? Yes?
Realistically, how would you find the density function?
Well, you could do it by experiment, by measurement, right? And like, let's say you're producing a certain type of material, right? And then you could take, various measurements within the production process to kind of say like, hey, if we do this temperature, this pressure, then the density will be this. But if we start changing the temperature and pressure, now our density will change, right? So that you have some idea, right? You have some idea of what's going on. But it would have to be something either measured or somehow calculated beforehand. And it also doesn't have to be density. As the next example is going to be, is going to have to do more with like an electric field, which would be a little bit easier to measure. So there depends again on where you are, like what we're talking about. All right, here we go. A lamina is formed by the region bounded by these curves. The density at any point is given by, what is this Greek letter? Rho. Rho of xy is x times y. So the density at the point you're talking about is just the product of the x and y coordinates of where you are. So whatever your x coordinate is times whatever your y coordinate is the density at that point. That's been provided to us. We didn't have to measure it. And now we want to know what is the mass of this object. So let me first draw the lamina itself. It's bounded by a couple of curves. All right, heads up. This could hit anybody. It's feeling bad. Yeah. All right. Yeah, thanks. Yeah, it wasn't, but all right, 1 minus x goes through the y-axis at 1, has a slope of -1, so it's that line right there. Right, that's y equals 1 minus x. The next one, y equals 1. Right, and then finally x equals 1. Where's that going to be? Let me see. If I plug in 1 here, 1 into there, that gives me the y-intercept of this. So yeah, that's it right there. It's x equals 1. The lamina is the region bounded by those curves. So my lamina is that thing in the middle there, right here. And my density function is xy. So I'm going to call this region, let's call it D. Have y'all noticed I just kind of like switch between D and R? Like it really doesn't matter. Region, domain, however you want to look at it. Let's call this D. So what I need to do is the double integral over D of the density function with respect to area. So that you're taking the density times the area to get the mass, and then you're adding all those masses up. Looking at that region, D, you're now equipped with Cartesian, right? You can do Cartesian rectangle. That's not a Cartesian rectangle. You do type 1 Cartesian, type 2 Cartesian. You could do polar, although that doesn't look polar, right? So we have to kind of like figure out what the best thing is for this. And I think just keep it in Cartesian, right? Type 1.
Yeah.
Let's go type 1 Cartesian. Yes?
The question obviously would be horrifically inefficient. Could you not convert it to polar, even though it's not technically circular?
Yeah. I mean, but you would have to figure out if you can define that somehow in polar, which wouldn't be easy to define.
Okay.
Yeah.
Just curious.
Yeah, there's some way to get from one to the other, but that's why we have different coordinate systems, is that we want to be able to make some things easy, some things, that were hard are now easy.
Because that would be terrible.
Yeah. Okay, here we go. I'm going to put the restrictions here. X is between 0 and 1. And the y value is bounded between two functions of x. The bottom function is that one, 1 minus x. And the top function is the constant function 1. Everyone understand those bounds? The x is between 0 and 1. Yep, 0 and 1. And the y values are stuck between those two functions of x. And then we just set up the double integral. So it'll be integral, go from 0 to 1. I do not have a choice there. It must be 0 to 1. 1 minus x to 1. It's a type 1, so I have to do the constant, the variable with the constants on the outside. I am integrating the density function, which was given to me to be xy. And we're integrating that with respect to y and then with respect to x. Right, there's no r that comes in here. Right, we're not in polar, so. Good? Do we really want to do that? I think that would be a pretty easy thing to do, yes? Let's use the computer, all right? Because I don't think you want to do it. I don't want to do it. So I'm going to go and do this double integral using the computer. Double. Zero to 1. 0 to 1. And then we're going to go 1 minus x to 1. And then x times y dy dx. Oops, dy dx. Now we need this answer because we're gonna continue with this problem. So I need this answer. Fit 5 over 24. Okay. So the mass of this object, I'll put it over here. The mass of this object is 5 over 24. Let's look at the next question. Oh, I need to go back up to the notes. Oops. Total electric charge. We were just talking about the mass of the object, right? If we change the wording of the problem, where instead of me giving you a lamina and giving you the density at every point, if instead of me giving you the density at every point, I give you what's called the charge density function, which I guess when you move on electrical engineering analysis type class, you'll understand a little bit more about what charge density is. I'm not here to discuss that in detail, but it's somewhat like a mass density, like density with mass, but you're talking about electrical charge instead. So let's say that I tell you what the charge density is at every point here, right? Then if you could sum those up, you get the total electrical charge on the lamina. It's the same exact problem though. It's the same thing. It's the double integral over that region of the charge density function times the area. Or with respect to area, I should say. And so if I ask you example 2, or if I tell you in example 2, charge is distributed over a region bounded by these curves, right? And I give you that the charge density function sigma of xy instead of rho is xy, then what's the answer? Same exact thing, but now it has a completely different meaning, right? This is mass. The answer to that would be your total charge, right? So it would be the units that you're measuring the charge with, right? Where that's going to be a measurement of mass, which could be in what, kilograms or something, right? So the point is that the math, again, is the tool, right? What you're doing with it depends on what class you're in, right? If you're doing physics, then you're maybe talking about mass. If you're doing some sort of electrical engineering class, maybe you're talking about charge, right? So it varies, but the tool has to be in place before you can do any of that. All right, that's the first concept, how we find mass. The next concept is about something called the moment or moments about an axis. So moment is a weird name for something. It's calling something the moment. All it is the mass of an object times the distance from some axis. So if I take, let's say, the x-axis here, and at some point I have a mass right here, right? There's a point, this point right here has some mass to it. If I were to take the distance from that point to this axis, call that the y-coordinate, if you take that distance and you multiply it times that mass, then you get what's called the moment. I should say not the mass, the density, sorry. Density, hold on. No, it's mass. Density times the area. So you get mass here times the distance, that's your moment. That's the definition of it, okay? I'm not here to explain like, oh, where's moment used? I'll explain it. We're going to talk about moments of inertia next, which has a better physical representation. So that distance times the mass is called your moment. Your moment about the x-axis, because I measured from here to here. Now, if you want to do that same point, but now you want to do the measurement from here to here, that's going to be some x value. That's the distance from the y-axis to your point. That's called the moment about the y-axis. This times the mass is the moment about the x-axis. This times the mass is the moment about the y-axis. Two different values. So what we do now is we say, what if we take all the moments, right? All the moments at every point. Let's add up all the moments about the x-axis. Or at every point, let's add up all the moments about the y-axis. then we get what's called the moment of the lamina about the x-axis, or the moment of the lamina about the y-axis. And you can see in the definition, it's almost the exact same double integral we just did. So this first definition says the moment of the lamina about the x-axis. So x-axis, which means when you go up to your point, that's a distance y, right? The moment about the x-axis, that's the notation we use for it, capital M subscript x, is the double integral over d. Recognize this part on the side? That's what we use to calculate mass, right? Now all we do is we actually multiply everything by y, which was that distance. So you're doing the mass at each point times the distance that point is from the x-axis. And you add them all up, and that gives you your total moment about the x-axis. Similarly, the moment about the y-axis is the same formula, except now you put an x here because you're trying to find distance from the y-axis to your mass. Now, why is the moment important? Well, the moment's important because you need the moment to calculate the center of mass. So I'm now going to give you the actual definition, definition of the center of mass. So if you have a lamina and you want to find its center of mass, we denote that as a point, x bar, y bar. That is the center of mass of your lamina. And remember, this is a non-uniform density, so you can't assume it's the center of the object. It could be somewhere else. To calculate the x bar and the y bar, you have to do them separately. First you find x bar, the x coordinate, then you find the y coordinate. To find the x coordinate, you take the moment about the y-axis and you divide it by the mass. We already found the mass, right? You're going to take the moment about the y-axis and divide it by the mass. Or there's your moment about the y-axis, and then multiplying by 1 over m is the same as dividing by m. So that's the calculation for the moment, the center of mass for the x coordinate. And then for the y coordinate, it's the moment about the x divided by mass, which is this integral. Yes?
Wouldn't that just be the derivative, the integral of your x?
Your integral of your x.
If you divide your moment by the mass,
Isn't it what?
isn't it just that integral of x that's inside then?
This is a different integral now because we've introduced an x next to this density function,
Right, 'cause it
which
was-
means the integration is going to be different.
Right.
It's not a constant. We can't pull it out. Yeah. All right. Shall we get the center of mass of that lamina that we started with? I have 10 minutes. Let me see. Yeah, let's do that. So let's go back to this one right here. Let's find, here I asked you to find the total mass, right? Let's find its center of mass. So to find the center of mass, I need x bar and y bar. X bar is the moment about which axis divided by mass? Moment about the y-axis. Right? Which for us is 1 over the mass times the double integral over that region D of, so what's the formula for moment about y? So think of the y-axis. Think of your distance from your y-axis to your mass. That means in the formula I'm going to have x. And now the density function. What's density function? Xy, rho of xy. I'm just going to put xy here because that's my density function, right? And then dA. Which for us is, what's 1 over our mass? 24 over 5. The reciprocal of that, 24 over 5, not 25 over 4. 24 over 5. Double integral. Now, that's the same area, that's the same lamina, right? So it was 0 to 1, it was 1 minus x to 1, and now, instead of it being xy, it's x squared y dy dx. You'll see? There's just one little tweak. We had to throw an x in here. But that's going to change the antiderivative, and it's going to change the answer, right? So I'm going to go to the computer. I'm going to go to the computer and I'm going to have it do that for us, okay? So I'm going to go up here and all I'm going to do is change that to x squared. And that should give us 3 over 20. That is just, I had the computer do just this. So I get 3 over 20. And then I can clean this up, I think. What goes in there? 4 goes in there 5 times, 4 goes in there 6 times, so 18 over 25. That's the x-coordinate of the center of mass of this lamina. Right? That's the x-coordinate. Now I want the y-coordinate. So to get the y-coordinate, I do the moment about the x-axis divided by mass, which is 1 over the mass times a double integral over the region D of this time, instead of x, y, right? So y times the density function with respect to area, which is 1 over the mass, we already said, was 24 over 5 times, now that integral is the same thing, 0 to 1, 1 minus x to 1, and then this time xy squared dy dx. Again, very similar to the integral we just did, but it definitely gives you a different answer because you've got a y squared instead of x squared. Change it in here. Where is it? Hey, we got the same thing? We got the same thing. 3 over 20 again. Yes?
Real fast, what are you hitting to go to exponent real fast?
The caret above the 6, the little arrow thing. Yeah. 3 over 20. Again, right? Does that make sense that it should be 3 over 20? Yeah. I mean, there's a lot of symmetry in this problem, isn't there, in terms of the region is symmetric. The density function itself, xy, is very symmetric. It's not always that case, though. All right, don't always think that your x bar and y bar are the same answer. But we get the same here, right? 3 over 20. So our answer is 18 over 25 again. All right, good? We're almost done. Pardon?
I was going to say those 2 points that we found is the coordinates.
Those are the coordinates of the center of the mass. Yep. And so if we go back and we look at that mass, let's see, I never graphed it, but it was y equals 1. It was y equals 1 minus x, right? And then x equals 1. So what we're saying is that if you were to look at that, there's our region right in here, right? That the center of mass of that turned out to be at, where is it, 3 over 20? No, 18 over 25. 18 over 25. I did. Yeah, I did it twice, right? Computer's like, what are you talking about? Jeez. Oh my goodness. It's too helpful. There we go. That seems, I don't know, to me that seems logical because your density is, it's so uniform. Like if you draw the identity function, right, then everything is symmetric over that line, right? The density is symmetric over that line. Okay, I want to get to one more thing before we end this. I have 5 minutes. And that is the idea that we just used this idea of the moment, right, to calculate the center of mass. The next concept is something called the moment of inertia. The moment of inertia is actually a very useful quantity. Anyone know what a moment of inertia is? It has something to do with rotation. The moment of inertia is a numerical representation of an object's resistance to rotate about an axis. So it's a way to give a numerical value to whether or not something wants to spin around an axis or not. So like if I take, this will be kind of hard to do, well, I don't need that. If I take this yardstick, right, and let's say this is the y-axis and this is the x-axis, right? If I take this little yardstick and I say take this and rotate it around the y-axis, that should be pretty easy to do. If I get my finger and I push it, it should rotate pretty easily around there, right? As opposed to if I say rotate around the x-axis. Now, when I push it, it's going to take more force to actually, it doesn't want to rotate because the mass is distributed further away from that axis than if it's like this. Yeah? Kind of makes sense? The moment of inertia is an object's resistance to rotation about an axis. And the way we calculate that is this formula right here. So we have the moment of inertia about the x-axis, which is an object's resistance to be rotated. So if I take this lamina, look at this lamina, if I take it and I put it right here and calculate the moment of inertia, it'll calculate basically a number that's going to tell me how hard it is to rotate this around here. If I move that lamina up here, what do you think happens to my moment of inertia? Gets bigger or smaller? Bigger, right? Gets bigger. The closer I am to the axis of rotation, the smaller the moment of inertia is. The further away, the harder it is. It's kind of like, I am going to run out of room, or run out of time. It's kind of like this. If I take this door, right? If I go to open this door, if I push from here, I can do it with my finger, right? Yes? But what if I try and push from right here? Right? See y'all later. Get out of here. Right? I mean, it has something to do with that, like your position relative to the axis of rotation contributes to how hard it is to rotate something or not. All right, so look at the formulas. We have the moment of inertia about the x-axis. And then we have the moment of inertia about the y-axis, right? And then we have the moment of inertia about the origin. So that's more like, here's x, here's y. The origin is more like rotating it like across the diagonal. Wait, where's my diagonal? No, around this way. It's just, all it is just the sum of these two. This is I sub x. The formula, all you're doing is y squared instead of y. You know how m sub x was a single y here? Now you're going y squared. And then if you want the moment of inertia about the y, you just square the x instead of a single x. And if you want the moment of inertia about the origin, it's actually just the sum of those two answers. So we can calculate that with the computer right now, couldn't we? For that same